Hi, I'm Scott Vaughn and I'm going to do a video here on some real rocket science. This video was inspired by the 2016 movie Hidden Figures, and I'm going to really go through a derivation of the rocket equation. I'll look at the rocket equation that includes gravity and air resistance and nonlinear air resistance, and we'll solve that rocket equation with Euler's method. So one of the heroes in the movie is Katherine Johnson, who is in real life has been one of the unsung heroes of the early NASA program, doing a lot of the real rocket science, the real challenging math of figuring out how to get astronauts into space and then return them safely to Earth. And so in the movie, Katherine Johnson is played by Taraji Henson, and in the movie she uses Euler's method to calculate the landing position for John Glenn after orbiting the Earth. And from the Los Angeles Times interview with Katherine Johnson, written by Amina Khan back in January 2017, Amina writes, "There's this lovely part in the movie in which your character turns to old math, Euler's method, to figure out how to get John Glenn back down from orbit. Did that really happen?" And Katherine Johnson's answer in the article is, "It seemed logical to me. I could see in my mind what I needed and sort of work backwards." Well, I don't think that she really did actually use Euler's method. I think that in the answer that she was providing here to this writer, it was one of those situations where to say no and to get into the technical details would have been just not really appropriate. Perhaps at that time it was too complicated and too much to explain, and it was easier to say, yes, essentially I did, yes, essentially, but technically not really. So also I can support that by another article I found. This is from Oklahoma University. This is OU graduate makes sure Hidden Figures math adds up is the article I found. This is by Jacob McClellan from February 2017. And he writes, "To make sure the movie's math adds up, 20th Century Fox hired Morehouse College applied math professor and University of Oklahoma graduate Rudy Horn. He worked with the film's stars, especially Henson, on learning pieces of equations. And Horn played a small role in shaping the script. He helped director Theodore Melfi settle on using Euler's method to solve a particular problem in a scene in which Johnson figures out how to calculate the trajectory to bring John Glenn back to Earth." He really liked the concept, Horn said. Didn't expect him to, but he actually put that into the script. And so I think this is how I can explain what's going on there. I looked for some information that's really, I found this actual NASA technical note that has Katherine Johnson's name on it from September 1960. And in that technical paper on the determination of azimuth angle at burnout for placing a satellite over a selected Earth position, there's a point there I've highlighted where it reads, "Incremental changes from the desired latitude and longitude due to Earth's oblateness are included in the iteration for obtaining the azimuth angles of the two examples." So I would say perhaps Rudy Horn, that math advisor to the movie, thought referring to this iteration as Euler's method was in some way true enough to the spirit of the original work that Katherine Johnson did, and also would have some dramatic and poetic effect, connecting old math with new and highlighting the way Katherine Johnson could always rely on math, as you would see in that scene in the movie. And incidentally, the lead engineer in that scene calls Euler's method ancient. Really, it's not so ancient. Euler's method was developed in the 1700s, and math standards, that's not ancient. That's about 300 years ago. Truly ancient math was developed by the Egyptians and Babylonians 4,000 years, or even the ancient Greeks 2,000 years ago. That's ancient, but Euler's method, relatively recent in math standards, and a fundamental principle that's taught in differential equations. When you first learn differential equations, which is really part of calculus, it sort of
So yeah, this is a video on Calc 2 topics and differential equations. We'll look at Euler's method, which is a topic of differential equations, and also a topic for physics. We'll actually derive the rocket equation and include gravity and air resistance. And when I do the air resistance, I'll put a term in there that includes nonlinear air resistance, which means that you couldn't solve this equation exactly. You need some method for a numerical approximation, which is precisely what Euler's method is. That's what it's for, to solve equations of this type. So it'll be a really good example of using Euler's method. And we can look at also solving the same equation with ND-solve on Mathematica for a comparison with the results that we do in Euler's method. All right, so we'll start the math, and we'll begin with Newton's second law. Force is mass times acceleration, but it can also be written as a time rate of change of momentum. And I'll set that equal to 0 because I'm going to say that in this derivation I'm going to have the sum of all forces equal to 0. That's equivalent to having momentum conserved. What I mean by that is that the momentum doesn't change. Its change over time is 0. Its derivative with respect to time is 0. So we can write that as an initial momentum, mass at time 1, velocity at time 1, equal to some mass later at time 2, and velocity at time 2. Now let's break up this part into, we'll go with mass of a rocket and some incremental mass that is exhaust. That is the initial mass. That's times some initial velocity of the rocket, and then at a later state, a second point in time, I'll express that as the mass of the rocket times velocity, but some change in velocity, plus some momentum due to the exhaust that's been expelled, and I'll write that as the differential amount of mass times some velocity due to the exhaust, the actual velocity of that exhaust. Okay. So this is all the momentum at a later state, the m2 v2, and this is all the initial momentum, but those momentums equal because the change in momentum over time is 0, because the sum of all the forces on this system are 0. The sum of all the forces is 0, so there are no external forces right now. I can draw a picture to better explain what I'm talking about. So let's begin with a rocket that's just moving through space. It could be in the atmosphere, in the Earth's atmosphere, any planet. It could be affected by gravity or not, but let's just begin with just perfectly simple idea of a rocket moving through space with some mass, and right here it's including some incremental amount of mass that it will eject later, and it's moving with some initial velocity v that actually could be 0 or non-zero velocity, could be in one direction or the other. And then we'll take a point later in time where the rocket has expelled exhaust. So it's expelling this differential amount, this incremental small amount of mass with some velocity of the exhaust. So the exhaust mass is moving with this velocity VE. The rocket has just the mass of the rocket that remains without that differential mass that's been expelled, and now it's going to move along with some velocity that it had plus some change in velocity. So I can maybe better define all of these little variables here just to be clear. This is the mass of the rocket. I'm going to call that some incremental change in mass, some quantity of mass that's been expelled from the rocket. It's ejected as exhaust. And then there's the velocity of the rocket. That would be the initial velocity. Then we also have this velocity of the exhaust. And the way that I'll measure that velocity of exhaust is from an observer reference frame. Talk about this more later, but just at the moment, we'll just think about that as if we were watching this rocket fly by. This is the velocity that we would measure, and it would be in an opposite direction of the direction of the rocket. So it's from the point of view of an observer that is outside of the rocket, that is watching that exhaust move. It is the change in the distance, the change in the position over time of that exhaust. It's the velocity of that exhaust. It would be in opposite direction. It might be, for example, we'll say that's negative, whereas this velocity is positive. And so finally I have this quantity dv that is this change in velocity. Yes, so there we have it. The variables mr, mass of the rocket, dme, this incremental change in mass, that is the exhaust, the mass of the exhaust that's being expelled from the rocket, v, the velocity of the rocket, or actually the initial velocity of the rocket, ve, the velocity of the exhaust that's coming out, the actual velocity that it's moving at in the observer frame of reference, and dv, the change in velocity of the rocket. Now there's one more variable that I want to define, and that is, I'm going to call it VE star. And this will be the relative exhaust velocity. What I mean by that is it's the exhaust velocity as seen from somebody in the rocket's frame of reference. Maybe to better understand what's going on, let me draw one more picture here. So let's imagine that in the situation that a rocket is moving along and there is exhaust being expelled. The rocket is moving this way with some velocity v. Well, let's suppose that the velocity is positive. And let's suppose that this exhaust velocity is negative because it's in the other direction. And I'm going to write the equation that the relative exhaust velocity from the rocket's frame of reference is, so the way that I'll define that is that the velocity of the exhaust relative to the rocket is just the velocity of the rocket minus that velocity of the exhaust in the observer frame. So you might think of an example. Maybe we could use some numbers here and say, suppose that the rocket was moving along at some quantity like, let's say, 30 meters per second. And let's suppose that the exhaust was being expelled, let's say maybe 100 meters per second, but it's in the other direction. So I'll say this is negative 100 meters per second. So that means I have 30 plus 100, 130. So from the rocket's frame of reference, the exhaust is moving away from the rocket at 130 meters per second. So this is always going to be a positive as long as the exhaust velocity is negative and the rocket's velocity is positive. Then I can think of this as being a positive number. So I will come back and use this some more later in my derivation. All right, so then let's go back and look at the equation that we have started to develop and study what consequences we can get from this. What we're looking at here is the mass of the rocket with the exhaust and its initial velocity. And as it expels exhaust, we have the mass of the rocket with its new velocity that's changed as a result, and the momentum of the exhaust, which is the mass of that exhaust and the velocity of that exhaust. So let's do a little algebra here. Obviously what we could do here would be to distribute the v. So we have the mass of the rocket times the velocity plus that incremental mass times the velocity equal to, and I'm going to distribute here as well. So I have mass of the rocket times velocity, mass of the rocket times the increment in velocity plus this increment in mass, velocity of the exhaust. Now you notice these terms are going to cancel. They're the same on both sides of the equation. The thing I want to do next is put this term and this term on the same side because they both have this differential in the mass that's from the exhaust. So why don't we write it like this? We'll say dmev minus, if I subtract this term to the other side, and now I can factor out this differential in the mass. Let's write it as, now this v minus ve, this is exactly what I called v star, so I'll write that as dme ve star. That's the relative velocity of the exhaust. Relative, that is, in the sense of it's being the observed velocity of that exhaust from the rocket's frame of reference. So then what I could do at this point is say that that differential in the mass, that change in mass that's due to exhaust, that amount of change there is exactly opposite the change in the mass of the rocket, because the exhaust is what's leaving the rocket, reducing the mass of the rocket, and so the change in mass, the differential change in the mass of the exhaust is exactly opposite that differential change in the mass of the rocket. So I'm going to replace this with negative differential change in mass of the rocket representing an equal amount to the differential change in the mass of the exhaust. Multiply that by velocity of the exhaust relative to the rocket. Mass of the rocket times some differential change in the volume, differential change in the velocity. So I think what I'll do now is make note of an assumption that I'll take that velocity of the exhaust for now to be constant. So if that's a constant, I'll put that as a negative VE star. Differential in mass of the rocket is some mass of the rocket, which changes over time, times some differential in velocity. Now, because this is the differential in the mass of the rocket, and here I have the mass of the rocket, I'm going to divide that over to the other side. This is a point in the differential equations class where you would call this a separation of variables differential equation, where I have differential in the mass of the rocket, the differential in the velocity, and I can separate those two differentials and then integrate both sides of this equation. So what's happening is I'm integrating over the interval of the engine burn. That would be from like initial velocity. So during that engine burn, that interval of engine burn, I'll go from an initial velocity to a final velocity, and from some initial mass to some other final mass, right? So this would be mass of the rocket equal to whatever its initial mass is up until the end of the engine burn, when the mass of the rocket is at its final mass on that interval. And here I'm integrating over the interval of the engine burn, which would be with respect to velocity, from some velocity equal to some initial velocity, when the velocity at the end of the interval is equal to some final velocity. So again, this relative exhaust velocity is a constant, and so integrating with respect to the mass of the rocket, this function, 1 over mass of the rocket, we get the ln function. And we'll evaluate at the endpoints of that interval, and integrating the constant function 1 with respect to velocity, we get this function for the velocity, which I'll plug in the endpoints v0 and v equal vf. Now, of course, the mass of the rocket is positive, and plugging in these two values, well, let's write it out. It's going to be minus ve star ln of the mass of the rocket, which I'll take positive, minus, and there's a negative in the function here in the antiderivative, so this is minus ve star ln with mo plugged in. And this would be final velocity minus initial velocity when you plug in those values. So we can write this minus ve star ln mass, final mass, plus ve star ln, that's initial mass. And this can be written as some change in the velocity, delta v. Now why don't we factor out this ve star that is in both terms, and then I'll write it as negative ln mass final plus ln mass initial is this delta v. And so I can combine these two ln's into one single ln. Let's go ve star ln, and this is, since this has a negative, it'll go in the denominator. That's m0 over mf. All that equal to delta v. And there it is. That's actually the rocket equation that I was attempting to derive, and I now have it. So we have delta v is the change in velocity, ve star, this is the relative exhaust velocity in the rocket's frame of reference, and m0, initial mass of the rocket, mf is the final mass of the rocket. So this is it. This is the rocket equation. It describes some change in velocity that is due to the velocity at which the exhaust is being expelled and the difference in the masses as that exhaust is expelled between the initial mass and the final mass. So you can think of it as some case where I have this rocket just moving through space, and it expels a little bit of exhaust, and as a result there's a change in velocity. And when it does that, there's this change also in the mass of the rocket. This equation, as it's written here, is what was derived by Tsikolsky. I think I'm pronouncing that close enough. This is a Russian scientist in 1903. I think what's really fascinating and interesting about this is it gives a mathematical and physics justification for the principle that a rocket could move in space. It doesn't have to push against an atmosphere. It doesn't have to push against anything. Simply the conservation of momentum is what causes a change in the velocity when there is exhaust being expelled. If there's a change in the mass and there is exhaust velocity relative to the rocket, there will be a change in the velocity of that rocket. If it's in an atmosphere, if there is gravity, that's all true, but it's also true in space. So we have this sort of mathematical physics explanation as to why rockets can work in space, and that was a hugely important step in the early 1900s as to the development of rocket science. All right, let's look again at this rocket equation. Delta V is VE star ln. We've got initial mass of the rocket, final mass of the rocket. This we could call the ideal rocket equation because it's just the simple, pure expression of what makes a rocket go, how the change in velocity is a result of this relative exhaust velocity, relative from the rocket's point of view, and the change of the mass of the rocket from initial to final mass as the exhaust is expelled with some constant. This is constant in this equation, this VE star. If I just take that to be constant, I'll simplify the work here. And that relates to the change in the velocity. So I'm going to rewrite it just for a little more analysis. I thought it might be interesting to say, if we flip this initial mass, final mass, we could take a negative out, and I want to do that just for a minute. Final, initial, because I want to call this ratio final mass divided by initial mass, and that way I could look at a picture. So if I make this the axis for this ratio of the mass, the final mass to the initial mass, and make this axis some velocity, can look at the difference in velocity and how that's affected by this mass ratio R. So one of the things we could notice is that if there was no difference between final and initial mass, if these guys were equal, the ratio R is 1, so we put 1 right up here. That'd be like 100% of the final mass is 100% of the initial mass if they were equal, and that gives me an R of 1. And an R of 1, if you take ln of 1, you get 0. So we'd have 0 change in velocity if there was no change in the mass, right? And then graphing this function, I'll set up axes like this, where I have velocity on the vertical scale, mass ratio on the horizontal scale, and I know that one point I have in the graph would be 1, 0. Now graphing a negative ln, if I assume a relative exhaust velocity of positive, then I've got a negative ln function, which on an interval less than 1 would have a shape like this. So the curve would move something like that. That's a graph of the rocket equation. Well, the negative of it. And so you could start to see how it's necessary to have mass ratios where the final mass is maybe some small fraction of the initial mass. So if we look at values for R, we might have 0.5 here and 0.1 back here, but it's necessary to have the final mass a small fraction of the initial mass in order to get these higher values of delta V, which is why, well, for example, to get a rocket into orbit, it has to be going really fast at a very high altitude in order to stay in orbit. And so the final mass has to be much less than the initial mass in the design of the rocket in order to produce a large velocity. All right, well, let's move on now. I want to go back to this equation I had earlier, negative VE star, differential mass of the rocket, is mass of the rocket times the differential in the velocity. So this is a differential equation that relates changes in the velocity with changes in the mass, which is where we derived we derived from this the ideal rocket equation. And this was a direct consequence of that conservation of momentum in the system, and that there was assumption of no other external forces. But now I want to add in external forces of gravity and air resistance, and so I no longer have a constant momentum in this system because of these other forces adding into the model of the motion of the rocket. So let's say that if we assume gravity and air resistance, then there's going to be a additional term that is some change in momentum due to these other external forces. So let's write it like this. So this dp is some change in momentum in the system due to external forces, which will be this gravity and air resistance. Well, these are all terms whose units we can describe as units of momentum, right? This is some mass times velocity, that's momentum. This is mass and velocity momentum, and this is a term that represents some change in momentum. And those changes in momentum over time would correspond to forces. And so if we look at the change over time on this side and the change over time on this side, then we are looking at actually the forces that are involved in this particular system. So let's write this as this constant negative VE star times some change in the mass of the rocket over time. And this is mass of the rocket, let's say, times some differential in the velocity over time. I could divide either one of these by time. I'll divide this one by the change in time, plus some change in the momentum due to external forces, divided by some change in time. So now this is let's look at the units of this. This is, maybe we could express this as something like meters per second. Do some dimensional analysis here. And this would be maybe something like, we could say kilograms per second. So the units are really like maybe kilogram meters per second squared. And so this is a unit of mass, and this is the unit of acceleration. So there's my mass times acceleration, units of mass and acceleration. So a unit, this represents units that I could describe as force. Likewise here, is looking at maybe the units of this one, we've got mass of the rocket could be perhaps measured in kilograms. And this is the change in velocity, so that's really actually units of acceleration, right? It'd be something that perhaps could be meters per second squared. So mass times acceleration, and this change in momentum, this is units of force. Could be written in newtons or in kilograms, meters per second squared. All right, so units look okay. Thought that might be a good thing to sort of think through carefully there before proceeding. So now that I know that each of the terms here have units that correspond to units of force, that could be newtons, also could be pounds. So let's write it as negative VE star, mass of the rocket, change in the velocity over time, or the acceleration, plus this guy, he is some external force. Now remember earlier I had this VE star as V minus VE, where this was the velocity of the rocket. This guy is exhaust, and both are in the observer frame. So if you were observing the rocket, this would be the velocity that you observe measured to some fixed points in the observer's frame, and this is the velocity of that exhaust relative to fixed points and positions in the observer's frame of reference. So I'm going to put that V minus VE back into the equation here. So it's minus V minus VE, change in mass over time. So let's distribute this term. We'll have negative V, change in mass of rocket over time, plus VE, change in mass of rocket over time, equal to mass of the rocket acceleration over time plus whatever external forces might be involved. And now to put this into a form that might be convenient for the next step, I think I'll move this term over to the other side and bring this negative term over to the right side. So I'll say exhaust velocity times change in rocket's mass over time minus these external forces is mass of the rocket times the acceleration of the rocket, or the change in the velocity over time, plus the velocity of the rocket and the change in the mass of the rocket over time, right? So this term went that way and this term went that way. So I just switched them. And I could take a point here and just call this sort of net force that is equal to the derivative with respect to time of the mass of the rocket, the derivative with respect to time of the total momentum of the rocket and its velocity. Right, so if I took a derivative of the rocket mass with its velocity, I get this. This is like a product rule, right? You'd have the mass of the rocket times the derivative of the velocity plus the velocity of the derivative of the mass, and all that's equal to these forces that include this exhaust velocity and change in the mass of the rocket. So, right, the total force, let's say the derivative of the product of the mass and the velocity need to equal to these two terms. And maybe that's kind of a complicated point to try to sort out and to come up with. Another sort of point that I wanted to get to through this video is looking at this stuff on, let's say, Wikipedia. It gets pretty confusing trying to understand. I hope this is another way of looking at it that maybe helps a little bit in understanding, like, where does this rocket equation come from? So it's a derivative of the momentum that is the total force, the net forces of the system, and the net forces of the system can be described as these two components that involve actually the lost mass due to the exhaust and the change in the mass of the rocket. And of course there may be other forces, external forces like gravity and air resistance, that are also part of the net forces in the system. Well, at this point what I'll do is I'll take this side of the equation here and write it again. Mass of the rocket, change in velocity of the rocket, plus the velocity of the rocket and the change in mass of the rocket over time, equals the exhaust velocity times the change in mass of the rocket over time minus external forces. Well, so we have some mass that can change over time, some velocity that can change over time. Velocity, again, here, this is the change in the velocity, this is the velocity, and it can change. So obviously dv dt doesn't have to be zero, so this could be a changing velocity. Change in the mass of the rocket over time. This term right here is going to correspond to the thrust of the rocket. And this will be where we'll find gravity and air resistance. So we can call this thrust R. And the gravity, what I'll do is I'll say that's the mass of the rocket that changes over time times some, we'll put G here. Now actually, if this rocket travels far enough and leaves the surface of the Earth, then the actual acceleration will change as the rocket gets further from the surface of the Earth. So this g isn't necessarily constant. I mean, it isn't constant in a a multi-stage or any rocket that's going into orbit. It's going to be significant change in that gravitational value, the force of gravity, or the acceleration, I should say, the acceleration due to gravity and the force as well. But that g isn't necessarily constant, so we'll have to keep that in mind. Let's put also on here this coefficient of drag, and then we'll say its air resistance will be this term that is proportional to the square of the velocity. So as the velocity increases, you get more force due to air resistance, and that force is proportional to the square of the square of the velocity. And that's a very realistic. It just comes from the physics. That's the physics of air resistance. So that's a realistic mathematical description of the nature of air resistance and how that force grows with velocity. So these are the external forces. So I'm getting closer to a differential equation that we can actually plug in some numbers and actually solve. But the fact that we've got a v squared means that we'll have to get approximate solutions, because this is now a nonlinear differential equation in v. Right? If we solve for the velocity, we've got to deal with the fact that this is v squared. We won't be able to get an exact value. We write it one more time. This is mass of the rocket, change in velocity over time, and the velocity, and the change in the mass of the rocket over time is equal to some thrust due to the rocket minus the weight of the rocket, another unit of force, but it's in an opposite direction to the thrust, and then minus some other term that's of force that's due to the air resistance. So this is a nonlinear differential equation in v, and we can plug in some numbers and come up and look at some solutions. So now this is something I could call my rocket equation that includes the weight and the air resistance. If the rocket is in the Earth's atmosphere, it still has weight and it still has air resistance. And so what we have here is the change in momentum, the net force, and this guy, this is the thrust. It's a force. This is the mass of the rocket and the acceleration due to gravity, so this is the weight, and this is the air resistance, the force of the drag, the atmospheric drag. Okay, so here's our differential equation that we can solve with Euler's method. We need to use some numerical method like Euler's method to find some numerical solution, which is a way of saying an approximate solution. You can't do the integration to find an exact solution for this type of differential equation because of that v squared in there, making this a nonlinear differential equation of its form that we can't solve exact. So use Euler's method to solve for v, the velocity, in this nonlinear differential equation. So I'm going to choose some values. What I did was I thought about a model rocket that's one stage and a situation then where the gravity isn't going to change, the force due to gravity, the acceleration due to gravity isn't going to change very much. But even with a model rocket, I will assume that the mass of the rocket does change, just very small amount, very incrementally, but there's a small change in the mass of the rocket, and there's a exhaust velocity from that model rocket. Now, it's not a constant thrust, but I'll simplify to assume that there's this constant thrust with this constant rate at which the mass is burned. So the engine burns at a constant rate, the mass drops off at a constant rate, there is a constant thrust. These are not really constant, but they're things that I'm going to choose to assume constant to focus on some other ideas here. So I created this mass of the rocket as a function, 0.05 minus 0.002 t, where t is the time in seconds. And I'm measuring mass in kilograms, but for example, in this particular case, you could think of this as being 0.05 kilograms initially at time 0. 0.05 kilograms would be 50 grams, and that's about 0.11 pounds. So a very light, small model rocket. The derivative of the mass over time, the change in the mass over time, is this constant negative 0.002 kilograms per second. That is, in a second, I think it's going to drop 2 grams of mass. So it'll be at time 1, 0.48 kilograms. And that is about 48 grams. I'm going to take about 15 newtons of force for the thrust of the rocket. That's 3.4 pounds of force, just estimating what seems to look about right for a small model rocket. And I'm going to just sort of guess, make up. Really what I did was look at some results of the solutions and found a value that seems to match what I experience in launching a model rocket. So I picked the drag coefficient of 0.02. That's dimensionless. And so we could take these values now and plug into my equation. So there's the differential equation with the mass of the rocket plugged in, the change in the velocity over time, the velocity that we will solve for, and the change in the mass over time. There's the 15 newtons thrust. This is the mass of the rocket again times 9.8 meters per second squared. Another assumption that I need to make here is a constant acceleration due to gravity. I think if the rocket doesn't go that high, it's reasonable simplification here to keep that as a constant. So it's another reason why just using a model rocket for this one stage it allows me to simplify some things and focus on other things. And then I've got this 0.02 drag coefficient. V squared is the velocity that we don't know that we could solve for, because this is my differential equation now, nonlinear differential equation. But it's the type, as I said, that I wouldn't be able to, now I can solve some nonlinear equations exact, but not this one. Doesn't set, it's not a form which we could find an exact solution. So we'll do some rewriting to get it into a form where we can apply Euler's method. So let's write it like this. I'm going to distribute. Be careful about the signs. And then simplifying one more step. Now to use Euler's method, what we want to do is isolate this derivative. So I'll move this 0.002v term onto the other side. We can solve for v with Euler's method once we have that dv dt isolated. So yeah, so there it is. So that's what I will plug into my Euler's method formula to calculate velocity at different times over an interval of time. Just to maybe sort of remind you of how that works in Euler's method, I'll say that velocity at some n+1 increment is this dv dt value. Let's say, well, times some increment in time plus that previous velocity value. So we could say that the next value for the velocity is this function. So what the velocity was before, what the time was before, all that multiplied by some increment of time added to whatever the previous velocity was. So this is what you get from the differential equation, the dv dt. So I thought what we could do is to figure out what would be the velocity after about 1 second. So I know that I'll assume that the velocity at time 0 is 0, and I'll say that it burns out, the rocket engine burns out in about a second. So I want to know what the velocity is at time 1. So I can use this initial condition, use Euler's method with this particular differential equation and figure out the velocity after 1 second. Okay, so then this is actually putting that differential equation into Excel to solve with Euler's method. And you can see that I have here isolated dt, the acceleration of the rocket, which is the change in velocity over time. And it's expressed in terms of the velocity, in terms of all the forces and change in the mass. And so this was the differential equation that we're solving for the velocity over time, given this initial velocity at time 0 is 0. So with that differential equation, I create this n value that is increments, that I do this iterative process of Euler's method. X sub n here, these xn values, this is increments of time. So I'm counting in hundredths of a second, and I had at time 0, the velocity is 0. And then you can see here that I'm taking the previous velocity, and I'm adding to that the value of the derivative using the previous velocity and previous time. And multiplying all that right there, that is the increment. That's the delta t, the step size, which is right here, this 0.01. So 1/100th of a second step size is what I'm using. So there I can see the velocity growing over time, and I ran through 100 steps, in each of them 1/100th of a second, so that I could find the velocity at 1 second. So it's about 27 meters per second. What was kind of interesting to discover is that the velocity shoots up pretty quickly within the maybe 12/100ths of a second, but then it really doesn't get any faster, even though it continues to produce thrust. That rocket continues to produce thrust. Perhaps its weight and its velocity and air resistance really cause it to reach a terminal velocity before the engine burn is complete. So it sort of maxes out at about 27 meters per second for the velocity. 27 meters per second, you can look up, is about 60 miles per hour, and so that seemed to be a reasonable conclusion for me. I thought it fit pretty close to what it looks like, and so then I also typed this equation into Mathematica to look at a solution there. And this is the result of a calculation in Mathematica. It's solving the rocket equation for velocity with given weight, thrust, and atmospheric drag. I used an initial mass of 50 grams, 0.05 kilograms, or about 0.11 pounds of weight, and final mass at 48 grams, the mass burn rate about 2 grams a second, or 0.002 kilograms per second. I used that thrust of 15 newtons, about 3.4 pounds of force, drag coefficient 0.02. Assuming the drag is proportional to the square of the velocity, I'm going to assume the engine burns out at 1 second, and so I find that the final velocity is about 27 meters per second, about 60 miles an hour, using this calculation also in Mathematica. So this is storing in this variable SOL for the solution a numerical differential equation solve function on that particular function that we were analyzing on the interval 0 to 1. This just gets the computer to return the value at 1 of the function f, and I get about 27. And I get the same graph I had with Euler's method. So that's pretty satisfying that it came out to be the same thing. All right, and that is the end of the video. I hope that was helpful. I hope it was helpful and interesting.